Welcome to Texas State University's Chemistry 2330 Introduction to Organic Chemistry. I'm your guide, Dr. David Irvin. Today we are going to begin Chapter 2, Acids and Bases, and this will be video part 1. Okay, so acids and bases are traditionally used in chemistry, and both inorganic chemistry and organic chemistry. So we're going to start with the definitions of different acids and how we can use them in organic chemistry. Okay. So the most traditional definition of acids and bases goes with the Arrhenius acid, which is an acid is something that dissolves in water to produce hydronium ion, or a positively charged ion. And a base is something that dissolves in water and gives us hydroxide ions, or the OH minus definition. Okay, so this was slightly changed to say that we produce not the hydronium ion, but the H plus in aqueous solution. We know that H plus doesn't really exist by itself and actually forms immediately to give us the hydronium ion, or H3O plus. Okay, so Arrhenius acids require it to be reacting with water. Okay. Okay, so an example of that would be like in organic chemistry, where we took HCl, or hydrochloric acid, and dissolved that in water to create the hydronium ion and chloride ion in there. Okay, so in this case, the HCl breaks apart. The hydrogen is donated from the HCl to the water molecule, giving us the H3O plus, or hydronium ion. And then the chloride ion is the counterbalancing anion in the solution here. Okay, so in this case, HCl is an acid because it generates hydronium ion. Okay, in the case of an Arrhenius base, we have to have things like potassium, sodium hydroxide, or magnesium, etc. When we dissolve this in there, we have the hydroxide ion form. When the hydroxide ion forms, it gives us a counterbalancing positive charge, typically the metal, like sodium or potassium is our counterbalanced positive charge, okay? So we can actually have reactions to form bases with the absence of a metal ion. In the case of ammonia, ammonia can accept a proton from water. It'll act as to accept that proton, still generating that hydroxide ion in water. Okay, so technically that makes it a Arrhenius base. Okay, so in all cases, when we react an Arrhenius base with an Arrhenius acid, we end up generating the formation of positively counterbalancing charge. In this case, ammonia forms the positive charge as the ammonium cation, but we still generate the hydroxide, making it a true Arrhenius base. Okay, so now I want to talk about a different type of acids and bases that do not require water. Okay, so this is a little more general. Arrhenius must have water, so let's go to a little more general, where we have what we call a Brønsted-Lowry acid and base. So in this case, we don't have to have water, so that means an acid is something that can donate a proton, or an H plus, okay? And then the base is something that can accept an H plus, okay? So water is not part of the equation, so this makes it a little more closer to what we can use in organic chemistry, because we don't always have to have water in our systems in organic chemistry, okay? What this means is that if something is an acid and can donate a proton, that means we have once it reacts, it forms a new species. In that case, the acid becomes what we call the conjugate base, meaning that it was an acid, it has donated, now it is its conjugate base, okay? And we'll do that a little bit more of that later. And then that means that the thing that accepted the proton was the base. It has now become an acid because it has a proton it can donate. So it is now the conjugate acid, okay? So in the Brønsted-Lowry system, an acid-base reaction always has a proton transfer in the reaction. And whenever it happens, the acid becomes a conjugate base and the base becomes the conjugate acid, okay? Let's talk about that a little bit more, okay? So what we'll always have is these pairs, okay? So in the case of this right here, we have HCl as our acid. And in this case, this is our acid. And in this case, water is going to act as our base because our water here is accepting the proton. Therefore, our water is the base, okay? The HCl, hydrogen chloride here, is the one donating the proton. Therefore, it is the acid, okay? So once the HCl donates its proton, the other half of the molecule, the chloride, becomes the conjugate base, okay? The acid becomes conjugate base, okay? Now the water, it was the base because it's accepting the proton. But once it accepts the proton, it becomes the hydronium ion, which we know is an Arrhenius acid. So this base is now the conjugate acid. Okay, so that's how they work. And so that the hydrogen chloride and the chloride ion are the conjugate acid-base pair of the acid, and the water and the hydronium ion are the conjugate acid-base pair of the base. Okay, so the key here is that the acid becomes the conjugate base, the base becomes the conjugate acid. Keep that in mind. We're going to use that a lot in the system, okay? So we can do this with things that do not require water. Remember, Arrhenius requires water. In Brønsted-Lowry, all we have to do is transfer a proton. So let's take water out of the equation and do two other materials here. So we have ammonia here, which was used as a base in the Arrhenius system as well. And we have what we call acetic acid here. So acetic acid, as we talked about in the last thing, has this hydrogen right here that we can donate. It's the acidic hydrogen that we can have react. And so in this case, it has a proton to transfer. It has a proton to transfer, making it the acid right here, okay? Now, ammonia can accept that proton, and so it is the base. And so when it accepts the proton right here, it now has the positive charge on it, and it is now our conjugate acid of ammonia, okay? When we donate the proton from the acetic acid, it now becomes the conjugate base because it no longer has that proton, it has transferred that proton, and it is now the base because it can now accept a proton, okay? So this is why the conjugate acid-base system works, because it's in equilibrium. It can go back and forth. Once you donate the proton, this acid becomes the base. Now that it's a base, it can accept a proton and go back to being the acid. Once this can accept a proton, it becomes the thing that has the proton. It is now the acid because it can donate the proton back to become the base, okay? So that's why we have conjugate acid-base pairs, and that's why we typically have some form of equilibrium associated with, or we can go back and forth, back and forth, back and forth, okay? So when we look at this, we want to see where the electrons are going. So what we're going to do is we're going to use those curved arrows again with double barbs to show two electrons are moving and where those electrons end up forming the new bond, okay? So when we have this, we have a, to transfer that proton, it doesn't just float off into air by itself. What happens is the electrons from the base come out and reach out and start pulling on that hydrogen. And then the electrons that were in the bond between the hydrogen and the other atom can stop and stay on the atom that the hydrogen is bonded to. That's going to generate a negative charge on your conjugate base. And now that that proton is transferred, this was a neutral molecule. This is not transferring electrons. Therefore, it's gaining a positive charge. We end up with a positive charge on the conjugate acid, okay? So our acid becomes a negative charge, our base becomes a positive charge, okay? And it's all because of the electrons being used in the system. These electrons from the neutral molecule are bonded to this hydrogen, giving us a positive charge. These electrons that were in their neutral molecule are residing on the atom, giving us our negative charge. Okay, now because there's an equilibrium there, we can have things that are very strong, which are things that are almost always shifted completely to the ionized form. And then there are things that are not as strong, where that equilibrium shifts is not completely over to the product side, but is somewhere in between, or somewhere, so that it's barely acidic, or it's almost all ionized, or it's hardly any of it's ionized. The amount at which it's ionized is how we get the acid-base strength. So for example, our classical strong acids like HCl and HI are almost completely shifted over to the conjugate base side, where they're almost completely ionized. And so they are what we call strong acids, okay? As we move down in acid strength with our traditional acids, sulfuric, nitric, and sulfate and phosphoric, those are starting to get weaker and weaker acids, okay? And so as we go down that list, we can continue down until we get to things like carbonate, and then carbonate ion, bicarbonate, water, and then alcohols here. These have very little shifted to their conjugate base, and therefore that makes them weaker acids, okay? Now, the cool thing is that the stronger the acid was, that means that the conjugate base is not very strong, because it would rather be the conjugate base, okay? So that means the weaker the acid is, that means the stronger the conjugate base it has, okay? So they're equal and opposite. The stronger the acid, the weaker the base. The weaker the acid, the stronger the base. We're going to use this theory of a lot of different chemistry. So it's very important to know that a strong acid makes a weak base. A weak acid makes a strong base. Okay. So some things to note in that conjugate acid pairs things, okay? Anything that, if an acid can be positively charged, neutral, or negatively charged, okay? Acids can be any charge they have, as long as they can transfer a proton, okay? So it doesn't matter what the charge is, okay? Bases can be negatively charged or neutral, like in the case of water and ammonia. It can accept a proton, but it can be negatively charged or neutral, okay? And if we have more than one hydrogen that can be transferred, we can actually transfer more. For example, HCl only has one hydrogen to be transferred. Therefore, we call that monoprotic, or one proton that it can transfer. Something like sulfuric acid or carbonic acid has two protons it can transfer. They're diprotic. It can transfer up to two hydrogens. It's going to transfer one first and then one second, but it has up to two that it can transfer. And then we have things like phosphoric acid, which have up to three protons that can be transferred, okay? So acids can be positively charged, neutral, or negatively charged, but they can transfer protons. A base can be negatively charged or neutral, and the number of protons available to transfer tells us whether it's monoprotic, diprotic, or triprotic, okay? So let's look at one of our special things here, and we call it carbonic acid, okay? Carbonic acid is, you take CO2 and water, mix them together, and you end up with carbonic acid. Carbonic acid then can immediately react with water. Water is acting as the base to transfer one of the protons to. When we transfer one of the protons from the carbonic acid to the water, we get hydronium cation and the bicarbonate anion, okay? So that bicarbonate anion still has a proton on it. So that bicarbonate anion can react with another equivalent of water to generate the carbonate ion, which will now it's -2 because it's transferred two protons, and two equivalents of the hydronium ion. Okay, so it's transferred one proton first to create the bicarb and one equivalent of hydronium. It transferred the second hydrogen to water to create the carbonate ion and a second equivalent hydronium. Okay, that's why things will appear different places on that scale, because the carbonic acid has 2 protons. It's going to be more acidic than the bicarbonate ion that has 1 proton. So the carbonic acid is higher on the scale than the carbonate ion, but they're still both acids because they can still both transfer protons. Okay? So, and then to drive it home again, there's an inverse relationship between the strength of the acid and the strength of its conjugate base. The stronger the acid, the weaker the conjugate base. The more likely it's going to be shifted to that conjugate base side because it so much wants to transfer that proton. Okay, so if we look at HI, it's a very, very strong acid, making the iodine ion a very, very weak base. When we moved up to weaker and weaker acids, we now have stronger and stronger conjugate bases. Okay, that concludes chapter 2, part 1.